I want to talk about the specific example of the harmonic series because it sheds a lot of light on how to start thinking about convergence and divergence of series. So harmonic series is the series 1 plus a half plus a third plus a quarter and so on. So I'm just counting numbers as the denominators. Just write a few terms of this out. We can write this in summation notation as the sum from n equals 1 to infinity of 1 over n. And what we've talked about so far with series, we've said, well, if we can find a formula for the partial sums, then we can just take the limit of that formula, and if that limit exists, then the series converges. And if not, then the series diverges. But I also mentioned about this example that it's hard, there's not a nice formula. So there's not a nice formula for the partial sums. And this is, so we can't really sum the series directly. We can't actually find the value of this series if it converges. Remember, the partial sum is you just go from 1 over 1 plus a half all the way to plus 1 over k, and that'd be the kth partial sum. So we can't sum this series, and this is actually true for almost every series we think about. Geometric series are nice, but most series are not, in the sense of being able to find a formula for the partial sum. And so the best we're going to be able to do is to try to ask the question of whether it converges or diverges. So don't ask for the sum. Just whether it converges or diverges. And this is going to be true for a lot of series that we look at, especially over the next few sections. Okay, so let me give one argument. So I'm going to give two different arguments about what happens to this series. And one of them I like because it's just very numerical and I think it really lets you feel what's happening. The other one I'm going to give because it's actually more important and more generalizable. So let's give the build by halves argument. Build by halves argument. So what I really need to do is write out a bunch of terms of these of this series. So, oops. So let me just write out some terms again. 1 plus a half plus a third plus a quarter. I'm just going to sit here and write for a while. Hey, look, I can count 7th and 8th and 9th, 10th. I'm actually going to put some dots in here and skip to a 16th and a 17th and a few more dots and a 32nd, 33rd, and so on. And let's see what I want to notice. Well, this number equals a half, right? So I said this is called building by halves, so it's going to have something to do with a half. But if you look at both of these two numbers, they're both greater than or equal to a quarter, right? A third is bigger than a quarter, and a quarter equals a quarter. So this is greater than or equal to a quarter plus a quarter, which equals 1/2. So there's another half that I've built. Now, how can I get another half? Well, can I just take the next two terms? Maybe not. A 5th plus a 6th, it may not be big enough. But if I go to the next 4 terms, notice that the last one's an 1/8, and the rest are all bigger than, actually not sure why I'm using greater than or equal to, except that you can do it by default. But it's strictly, but each of these is, a 5th is bigger than an 1/8. It's more than an 1/8, right? A 5th is 20% and an 1/8 is 12.5%. So, and all these numbers with smaller denominators will be bigger than an 1/8. So this is bigger than an 1/8 plus an 1/8. A 6th is bigger than an 1/8, a 7th is bigger than an 1/8, and an 1/8 equals an 1/8. And so you actually get 4/8, which is a half. And maybe you can see now why when I did dots, I stopped at 16 and I stopped at 32, because if I take this piece right here from a ninth to a 16th, that's greater than a 16th plus a 16th. You know, each of these terms, 16th is the smallest term in this little sublist from a ninth to a 16th. So it's each individual term is going to be bigger than or equal to a 16th. So I can write this, and from 9 to 16, there are 8 terms. So if I add a 16 to itself 8 times, I get 8/16, which is a half. And one more time, just to illustrate it. Oops, I went too far. I want to go from a 17th to a 32nd, right? 32nd is the next power of 2, and that's greater than a 32nd plus a 32nd plus dot 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 plus a 32nd. All the terms from 17 to 32, there's 16 numbers from 17 to 32, right? So that's 16 terms. So this sum, a 32nd added to itself 16 times, is 16 over 32, which is a half. And okay, so you have to take more terms each time, but you can always make it bigger than a half. Like if I wanted an argument that this sum is bigger than 5, well, let's see. Up to, this is 1, this is another 2, this is 3. So now we're up to 3.5, right? We know that if we add up to the 1 over 32, we're bigger than 3.5. So that's 1. This is greater than 1 because these add up to, these two add up to greater than 1. Oh, that's greater than a half. So the sum from 1 to 32 is 1 over 1 plus 1 over 2 plus 1 is greater than 3.5. If I wanted to get greater than 4, I just have to take another, 32 terms from 33 to 64, and so on. So this sum, I should call it S, as we've done in the past. This sum S, so S is greater than 1 plus a half plus a half plus a half plus a half. And we can keep building these for any number of a halves. I can stop somewhere. So I can say, okay, it's bigger than that number. Because I can always take enough terms to build another half. So let's say that's n times, or sorry, k times. Just want to use a different letter. Actually, I've even used k already. So let's use m times. And so this is 1 plus m over 2. But we can do this for any number of m we want. And therefore, we can make this sum as large, or it's, as large as we want. So this means S. This means S, number, for any number m we want, I guess I should say. And this means that S goes to infinity. So S goes to infinity. Therefore, the harmonic series diverges. So this is a divergent infinite series. Oops, diverges. And that's very important. So the harmonic series diverges. So that's the conclusion we can take from this. We can make this as big as we want if we're willing to just take a lot of terms. Grows slowly, but it still grows. And that's actually something very important here, is that this is sort of surprising. This might be sort of surprising that we've seen geometric series, as long as the R is going to 0, as long as the terms are going to 0, sorry, the R is a fixed constant. As long as the term, if R is less than 1, then we have R to the n inside geometric series, and those go to 0 if R is less than 1, and then the series converges. But here, so notice the individual terms go to 0, and yet the sum still diverges. And that's why this is very subtle. It's sort of subtle in the same way that we saw with improper integrals, and we're going to make that connection explicit in a moment. the individual terms go to 0, but the sum, right, because 1 over n gets smaller and smaller, so you're adding less and less each time, so that's what I mean by the individual terms. I mean 1 over n. But the sum goes to infinity. So it's amazing because you're adding less and less, but it never quite comes to a stop. You would imagine that a sum, you know, when we do a half plus a quarter plus an eighth plus a 16th, we saw that that was coming to a stop. It was sort of the terms getting small rapidly and the whole sum's coming to a stop. But here, it's odd. You have to think about it for a while. You have to let it sink into your brain that the individual terms are going to 0. We're adding less and less at each step, but the total sum is still crawling off to infinity. Okay. So let me give a different argument that's going to be more, this is not very generalizable to other situations, but I do like this because it's very concrete and it becomes very believable, I think. But let me give an area argument. That this series diverges. So we can plot the sequence. We looked at this with sequences before. We can plot the sequence 1, a half, a third, a quarter, and so on. And if we plot it, it looks something like this, right? So here's an x and y axis. Let me just mark it off. 1, 2, 3, and so on. Let me just mark off enough terms. Let me put the vertical one way up here. So we have an x-axis and a y-axis. Just so I can plot these somewhat effectively. So I'm really plotting, we're plotting, you know, we're really plotting a sub n equals 1 over n. So we're plotting the points n comma 1 over n, right? So 1, we do 1, 1, 1. For n equals 2, we plot a half. N equals 3, we plot a third. Let's say that's there. Equals 4, we plot a quarter and a fifth, and it sort of shallows out, but it's getting closer and closer to 0, right? Keep going if we wanted to. So we can get these guys. And I can think of these heights, right? These heights as being the heights that we're looking at. And I want to add all those heights together, but as heights, it's a little hard to see what it's going to make, what it's going to become. So here's the tricky idea. Here's the kind of neat idea. Instead of heights, let's make a rectangle. So this rectangle has width 1 and height 1, right? And this rectangle has width 1 and height 1/2, which means it has area 1/2. Let me just draw some of these rectangles in and then I'll put the areas. So I'm going to draw rectangles, which should look like kind of rectangles you've seen before. It looks very Riemann sum-esque, right? And this keeps going. And so the area of the first one is 1 because it's 1 by 1. The area of the second one is a half. Area of the third rectangle is a third, a quarter, oops, a fifth, a sixth, and so on. So the area inside the green boxes is in fact the harmonic series. If we keep going forever, the green rectangles equals the harmonic series, the sum n equals 1 to infinity, 1 over n. Okay, now, but we've seen pictures like this before. So let me draw maybe the nice thing to draw, which I could have drawn through the orange points in the first place, which is, look, we have our nice curve here that goes through these points. And that is the function y equals 1 over x. And let's think about these. So we have the area of the green rectangles is the infinite series, and think about the area under the curve, right? There's your area under the curve. And so the area under the curve is the improper integral. Oops, I forgot to make this thicker. Okay, so the area under the curve is in fact the integral from 1 to infinity, 1 over x dx. And now here we have the green area is bigger than the red area, right? Got this green area here. Should have made this thinner. So got the green area that's kind of inside all of these. And the green area is bigger than the red area. Okay, so, but you know, this is exactly shows something. So the green area, green area bigger than the red area. Hopefully you're not colorblind, although I don't know if that means you couldn't tell the difference between these. Anyways, the green area is bigger than the red area, which means that the harmonic series 1 over n is greater than the integral, the improper integral. But we know how this improper integral behaves. It's the natural log function as it goes to infinity, which also goes to infinity. So this diverges. This improper integral diverges. And the harmonic series is bigger than it, so it also diverges. So this also diverges. Okay, and this is nice. This is an argument that we're going to be able to generalize, because we're going to basically compare a series to the improper integral that looks, oops, trying my infinity looked like an 8 right there, so I'm trying to make it look more like an infinity. But we can do this in general. So in general, we'll compare an infinite series. We'll just basically turn it into a proper integral and ask whether the improper integral converges or diverges. So it's going to help us. And that's what we'll do in the next video. But again, this example, the harmonic series, very important. And you should really focus on the weirdness of the fact that you're adding less and less at every step, and yet it's the sum is still crawling off to infinity. That, you know, 1 over n gets small. You know, eventually you're adding 1 over a million, and then 1 over a billion, and then 1 over a trillion, and you're adding almost nothing. And yet that sum is still crawling off to infinity. It's very strange. Takes some time to get your mind around. So spend some time dwelling on that, thinking about it. All right.